Hello and welcome to this video looking at the gas laws. We'll start off by looking at the definition of an ideal gas. We'll move on to the ideal gas equation, as this forms the basis of the derivation of all of the gas laws. And then we'll look at the gas laws in turn, namely Boyle's law, Charles's law and Gay-Lussac's law. So what is an ideal gas? Well, it's important to recognise that an ideal gas is a theoretical construct. Real-world gases don't quite behave like this, but it's a useful way to mathematically model gases. And there are three main assumptions made. The first of which is that the molecules themselves have no volume. They are infinitesimally small. The second assumption is that collisions between molecules are elastic, which means that no energy is gained or lost when molecules collide. And the third assumption is that there's no interactions between molecules. For example, there are no forces of attraction. Next, we're going to look at the ideal gas equation, which takes the form PV equals nRT. And this is an equation that's well worth remembering, as it forms the basis on which we derive all the gas laws. P is the pressure in standard index units of pascals. V is the volume in meters cubed. N is the number of moles of the gas, the amount of gas we have. R is the universal gas constant, which is just a constant number. It's got the value of about 8.3 and has some funky units. For the keen beans, it's the product of the Avogadro's constant and the Boltzmann constant. And T is the temperature in Kelvin. So for the ideal gas equation, you can see that we've got four potential variables. We could vary the pressure, we could vary the volume, we could vary the number of moles of the gas, and we can vary the temperature. Whereas the ideal gas constant is just a number and can't be changed. To derive the gas laws, all we do is make the assumption that the amount of gas we've got is fixed, so N becomes fixed, and then we take it in turn to fix either pressure or volume or temperature, and then see what that does to the other terms. And we'll start with Boyle's law, which states that at a constant temperature, the volume of a fixed amount of a perfect gas varies inversely with its pressure. So mathematically, you could write this down by saying that P times by V equals K, where K is a constant. And another way of expressing that would be to write that V is inversely proportional to P, which is this phrase here. And we can see that Boyle's law is actually just a special case of the ideal gas equation, where if our ideal gas equation here, PV equals nRT, what we're saying in the case of Boyle's law is that T we are fixing as a constant, and that's part of our assumption. R is already a constant and remains so, because by definition it's the universal gas constant. And assuming that we're not gaining or losing any moles of gas, N is also a constant. So P times by V is equal to the product of three constants, which will be a constant itself, which we can define as K, where K is N times R times T. If two different variables multiplied by each other will always come up with the same number, that means that if we make P bigger, V will have to become smaller. Or likewise, if we make P smaller, V will have to become bigger. So P times V being a constant is the same as saying that V is inversely proportional to P, or that V is proportional to 1 over P. So what does Boyle's law look like in practice? Well, imagine we've got a container here with a gas inside it, and on top we've got a plunger. If we push the plunger down, we will reduce the volume of the gas, and as such we would see an increase in the pressure of the gas. So plotting this graphically, if we plotted pressure against volume, we see an inverse relationship between the two, namely that as we decrease the volume of the container, we'll see an increase in the pressure. And if we increase the volume of the container, we'll see a decrease in pressure. Boyle's law also gives us a way to calculate the amount of available oxygen from an oxygen cylinder. So let's say we've got a pressurized oxygen cylinder here, and we open up the valve and release the oxygen. We've got a situation where we've got a starting volume and a starting pressure, and a finishing volume and a finishing pressure. Boyle's law tells us that pressure times volume is a constant, and so it follows that the starting volume multiplied by the starting pressure is equal to the finishing volume multiplied by the finishing pressure. The starting volume will be the volume of the cylinder, and the starting pressure will be the pressure within the cylinder. The finishing volume will be the volume of oxygen gas, which is released from the cylinder, and the finishing pressure will be atmospheric pressure. Let's assume the volume of the cylinder is 10 litres. Full cylinders within the UK are filled to a pressure of 13,700 kilopascals. The volume of released oxygen is the number we're trying to work out, so we'll keep that as V2. And atmospheric pressure is approximately 100 kilopascals. So if we rearrange that equation and solve it for V2, it gives us a volume of oxygen at atmospheric pressure of 1,370 litres. And just also remember that 10 litres of that will remain within the cylinder, and so your volume of available oxygen is 1,360 litres.